Since you're going to see something similar to this in the lab this week, thought I might take some time to go over the sort of classic Atwood machine problem. Now, it sounds sophisticated calling it an Atwood machine, but really it's just two masses on a pulley with a rope. So one goes down, one goes up. Just goes to show if you're lucky enough to discover something first or analyze it, you can get your name attached to it. So this is why history remembers the name Atwood. So we have two masses on a pulley. We're going to assume that one of them is more massive than the other, specifically that this mass M2 is going to be greater than this mass M1. So when the system is allowed to accelerate, then M2 will go down, M1 will go up, and we're trying to find its acceleration. Now, we're assuming that we have a massless pulley, which means we don't have to consider any torque or anything acting on the pulley. We'll come back and work on that in a different video. But the other important thing is that we have a tension that is throughout this rope. And if we have a massless pulley, then we have the same tension acting everywhere throughout this rope. In other words, I don't need a net torque to make this pulley rotate because I'm treating it as massless, and so I have the same tension throughout. So when I go and look at the free body diagrams for these objects, on mass M1, I'll have its weight M1g. I'll have some tension, T, pulling up like this, and that's going to give rise to an overall net force and acceleration in this positive direction here for M2. Similarly, we only have its weight M2 times g, and we have that same tension moving up here, but that's going to have an acceleration going down there. So the other important thing is that we have this rope here, and because the rope is present, we're going to have what we call an acceleration constraint. We saw these back when we were working Newton's third law type problems, and all we're saying here is that the rope is of some fixed length, some constant length that's not going to stretch and change its length, because if it did, that would make it a spring. So this means that when I look at the motion of these, right, if I say this is located at some y1, this is located at some y2, if M1 goes up by 1 centimeter, then Y2 has to go down by 1 centimeter, which means that their displacements, delta Y1, has to be the negative of delta Y2. And the negative just means they're acting in different directions, but they're going to have the same magnitude of displacement. And again, this is going to carry over to both velocity and acceleration. If this moves by 1 centimeter in 1 second, then the other one is going to move by 1 centimeter in 1 second. So V1 will be equal to the negative of V2. There's going to be a velocity constraint, and similarly, if we are changing its velocity, then its change in velocity A1 must be the negative change in its velocity A2. So this becomes a constraint equation between the accelerations of each of these blocks. They're going to have the same magnitude of acceleration, just acting in different directions. So this is just a force problem, or rather, we're first going to solve it as a force problem. We've already started by drawing our free body diagrams. If I were to look at block number 1, the only forces we have to worry about are vertical forces, not horizontal ones. So sum of forces in the vertical direction. I have tension that's pulling up, so that's going to be positive. I have weight pulling down, that's going to be negative. And this is going to be equal to mass times acceleration. Got to be careful because we're going to have different masses and different accelerations. This is also going to be one of those videos where I am not going to plug in numbers because we are going to get some cancellations and we'll be able to see more about the behavior. So this is the equation we get for our first block. And then we will have a similar looking equation for our second block. In fact, it's going to be the exact same one, except I'm going to replace all the 1s with 2s. T minus M2G equals M2A2. Again, we only have tension and weight. We're ignoring friction. We're ignoring air drag. So looking at this, we actually have 3 unknown quantities. Our tension is unknown, our acceleration A1 is unknown, and our acceleration A2 is unknown. We're assuming that the masses up here, that m2 is greater than m1, that those are known. If we had values, we could just go and plug those in. But we have these two equations here plus our third constraint equation. So we have three equations and three unknowns, which means that we have a system of equations. In fact, this is a linear system of equations that allow us to solve them. So sort of quickly going through how we do that, because this one isn't so complicated. Since I'm really only interested in the acceleration here, I'm going to eliminate tension as a variable. I could solve for it, but in the end I'm not going to. So I'm going to move m1g over to this side. This gives me t is equal to m1g plus m1a1. Same thing over here. I'm going to move m2g to the other side, and I get t is equal to m2g plus m2a2. Hey, that's nice. I have two different equations that say this is what the tension is, so I can just take these two equations and set them equal to each other. So this says that m1g plus m1a1 is equal to m2g plus m2a2. And so we have combined those two together and completely eliminated tension. Now, notice that we have a1 and a2, which are related by this constraint. And at this point, we could solve for either of the accelerations, either a1 or a2. Because a1 is going to be positive because it's moving upward, I want to solve for that one, so I end up having a positive overall acceleration. And so what I'm going to do is, if a1 is equal to the negative of a2, that means that a2 is equal to the negative of a1, and I'm going to plug that in here. So I have m2g plus m2 negative a1. We have to keep very careful track of all of these subscripts because we have a subscript on the mass and a subscript on the acceleration. But combining that together, we have m1g plus m1a1 is equal to m2g minus m2a1. Now we've got our equation down to only one unknown, and that unknown is just our acceleration a1. So I'm going to put everything involving a1 on this side and everything else on the other side. So I'm going to move this term over here, and I'm going to subtract that and move that term over there. So this is going to give me m1a1 plus m2a1, right? Because when I move that over, the positive becomes negative. On the right-hand side, I have m2g minus m1g. Because that was positive, I bring it over and it's negative. So notice immediately I can start doing some factoring. I have a1 in common with both of these terms. So this gives me m1 plus m2 times a1. Over here we have m2 minus m1 times g. And then if we want to then solve for the acceleration, I'm just going to divide by this term over here. So we get that a1 is equal to m2 minus m1 divided by m1 plus m2. So a couple things. Notice that overall this term here is dimensionless because it's a mass divided by a mass, which means my acceleration is just proportional to the acceleration due to gravity. This shouldn't be surprising since it is just accelerating due to the motion of gravity. But also notice how the masses come in. Since m2 is greater than m1, this means that my a1 is going to be greater than 0, and my blocks move as they should, meaning m1 goes up, m2 goes down because it is more massive. And then also notice if m1 was equal to m2, this means that my acceleration would be equal to 0, which is what I would expect. These two forces would exactly balance themselves. So this is what I have when we have a massless pulley. Now, sort of very quickly, we've seen that we can do problems in multiple ways. And so that way was using forces. We can also solve for the same acceleration using a method involving conservation of energy, in the same way we saw for some previous types of problems. Notice there we didn't have to worry about acceleration, but we did have to worry about positions and velocities. So there, again, we had some initial position and some final position, initial velocity, final velocity. Well, if my blocks start off not moving, then my V1 initial is going to be equal to 0, and my V2 initial is going to be equal to 0. But, again, because we have this constraint between how the rope moves means that my velocities are going to be equal and opposite, and my displacements are going to be equal and opposite. And that's going to come into play when we talk about the kinetic and the potential energy. So in other words, my V1 final will be equal to the negative of V2 final. They have to move at the same speed, just in different directions. And when I look at their displacements, the delta y1 will be equal to the negative of delta y2. And that's going to come into play when we talk about the gravitational potential energy. We already said we're going to ignore friction and drag, so we have no non-conservative forces, but we also had this rope here. However, if I look at the system, as consisting of both blocks plus the rope, and in addition to having a massless pulley, we sort of sneaked through above the fact that we're also going to have a massless rope. We didn't consider the forces acting on the rope to accelerate the rope. So it's not going to contribute to any of the energies, but since it's internal to the system, this means that the tension is not going to do any net work. So its work is going to be equal to 0. I'll make that an arrow. In other words, it transfers energy from one block to the other, but it doesn't actually do any net amount of work. So we only have the kinetic and potential energies of these two blocks to worry about. And I'm going to write this in terms of the changes in energy. In other words, I have the change in energy of my first block, which is going to be its change in kinetic energy plus its change in gravitational potential energy. So this is energy changes for block number 1. Then I have energy changes for block number 2, U2. And again, since we have no non-conservative forces, those are going to add up to 0. So this is my one equation that ultimately will lead to getting a similar sort of result up there. My change in kinetic energy, again, is always final minus initial, but in both of these cases, my initial is going to be equal to 0. So I'm just going to have 1/2 m1 v1 final squared, 1/2 m2 v2 final squared. I know eventually I'll be able to combine these together because they're going to have the same final speed. Change in gravitational potential energy, this is just, again, mg delta y. So adding in the right subscripts, we have m1g delta y1, m2g delta y2, and all of that is still equal to 0. Now I can start to use my acceleration constraints, because notice that I have v1 final, v2 final. Those are going to be the same value. I can just write that as a v final. Similarly, I'm going to have a y1, a delta y1, and a delta y2 that I can combine together, and there we will have this negative sign creeping in because of we're not squaring it or anything. So if I start rearranging some terms, notice everything is still on the left-hand side of this equation. I'm going to have 1/2 of m1 plus m2 v final squared plus, let's say I substitute in that delta y2 is equal to the negative, I'm going to say delta y2 is equal to the negative of delta y1. That's just flipping the sign over to the other term, and then combining that together is going to give me m1 minus m2 times g times delta y1 is equal to 0. Already you can start to see, since we already know the answer, where some of these terms are coming from. And then to connect this to the acceleration, we're going to have to use a kinematic equation. In other words, since we have a velocity and a distance here, which we didn't have in our overall expression up here, so I'm going to move that to the other side of the equation. That becomes negative, but I can assign that negative sign to this term in here, so it just flips direction. So this is just going to give me 1/2 m1 plus m2 v final squared is equal to m2 minus m1 times g delta y1. And now I'm going to start moving some terms around. In other words, I'm going to divide by m1 plus m2, and then I'm also going to divide by delta y1 on both sides. And this is going to give me v final squared divided by 2 times delta y1 is equal to m2 minus m1 divided by m1 plus m2, all multiplied by g. Now, why we do that is because this expression from our velocity displacement equation, in other words, can you see if I write over here? I think you can. V final squared is equal to V initial squared plus 2a delta y in this case. Notice that since my V initial is equal to 0, my a, if I were to solve for it, I just divide by 2 and divide by delta y, and so this gives me the same acceleration. So whether I look at this as an energy problem or whether I look at it as a force problem, I still get the same result. Again, this is the acceleration with a massless pulley for an Atwood machine. And so this is just to set the context for the next video, which is where we're going to give the pulley some mass, which is what you're going to be looking at in this week's lab.